specifying these parameters to specifying these parameters to different values. Oh, I should post the chat. Can I do that? No. Here are the slides in the chat. Yeah. So if you're clever at specifying these parameters to different values, then you get many different models. And so to show you how many you get, here's a chart from a paper by Borodin-Gorin-Wheeler. Here at the top, you see this stochastic colored six-vertex model. And then all the other things are what you get by taking limits in different ways. So there are some interesting things like ASAP, and there is the KPZ equation, Brownian percolation. I'm not going to talk about those, but those are pretty interesting things. And what this shift-invariance paper is doing is they kind of proved a certain symmetry of this model, and then they took a bunch of limits through polymers and then the KPZ equation, and kind of automatically they got the same symmetry result for all of these different models. And what I do in my paper is I prove a more general symmetry for this model, and then I follow all these arrows to get the corresponding symmetry statements in these limiting cases. And one advantage of taking such a general model is, well, first of all, it's very combinatorial. And second of all, at this level of generality, you can actually see relations to things like geometric RSK or the Positroid varieties in the Grassmannian, which I'm going to actually spend the second half of my talk on. But for now, let me just define the model for you. And the definition is very, as I said, very combinatorial. So what you do is you start with a bunch of, with n lattice paths, and each of them is going to have its own color. So here's a path of color 1, path of color 2, color 3, and etc. And they all enter this rectangle, and each of them is going to be a lattice path that kind of goes up and to the right, and then exits on the boundary. And so the way it is defined is it's a probabilistic model. So you essentially, whenever you see a square such that it's incoming colors, let's say here you have 4 and 5, then you flip a coin, and then either it's going to be a crossing or an elbow in this square. And so, and then the probability depends on whether, so the two colors are not going to be the same. If the smaller color comes from the bottom, then the probabilities are going to be P and 1 minus P. If it comes from the left, then the probabilities are going to be QP and 1 minus QP. So for example, here 4 is less than 5, so I'm in the top row of my table. And so if I choose that they form a crossing, then that happens with probability P. And now I have 2 more squares available. And for example, for the square on top, I have 4 and 6 as my incoming colors. So if I choose that it's an elbow, then that's what happens with probability 1 minus P. And similarly, I can choose then the other square is also an elbow. And now I have something that's interesting, because in this square, the bottom color is 5 and the left color is 4. 4 is less than 5, and therefore I'm in the second row of my table. So if I want these paths to form an elbow again, that's going to happen with probability 1 minus QP. And so you keep going until you fill all these squares, and then you get some kind of a pipe dreamy picture. Well, it looks kind of like a pipe dream, but there's a difference, because for pipe dreams are not allowed to intersect more than once, and here there is no restriction. So here's one intersection point of 2 pipe dreams, and here's another one of the same 2 pipe dreams. So they can cross many times, but then the probabilities are going to alternate between P and QP every time. So in particular, when you send Q to 0, you recover the ordinary pipe dreams. Now, I still haven't told you what are these Q and P parameters. So here it goes. Q is just a single fixed parameter that's fixed for all squares, is the same. And P is what is called the spectral parameter of each square. It's going to be different for every square. And the formula for P is given here. It's some kind of a ratio of two linear expressions. So you choose the x variables for your columns, and then the y variables for your rows, and then for every square, you're going to have xi to the bottom of it, and then yj to the left of it. And so these are the x's and y's in this formula. And this formula actually looks pretty weird, but then it shows up in Schubert calculus a lot, in McDonald theory. So that's actually, it's related to the R matrix of the quantum affine algebra. And this formula is the reason the model kind of works, because it satisfies the Yang-Baxter relation and it's integrable. And that's going to be important for the talk. So that's the definition of the model. Let me now try to state the main result. And so you have these pipe dreams. And then every pipe dream, of course, is going to give me a permutation, right? So there is the number of pipe dreams is a power of 2. Each gives me a permutation in the most obvious way, where you kind of look at the pipe that starts at P4, and then it terminates at Q10. So your permutation stands 4 to 10. No weird rules here. And then what I'm going to be interested in is not permutations, but it's what is called horizontal and vertical boundary conditions. So the idea is that you look at your pipe dream, and then you want to find all horizontal pipes. And the pipe is horizontal if it connects the left boundary of the rectangle to the right boundary of the rectangle. And in this case, there is 4 horizontal pipes shown in red. And what I want to do is I want to record their endpoints. So for example, if I have a pipe which connects a horizontal pipe connecting P7 to Q4, then I record 7, 4 in my set of pairs. And that's H. And then V similarly is going to be, I'm going to be looking for all vertical pipes which connect the bottom boundary to the top boundary of the rectangle. And that's it. So I have two sets of pairs, H and V, and now I want to, let's say I've just fixed 2 sets of pairs, and then let me define by ZHV the probability that I observe these as horizontal and vertical boundary conditions. So ZHV is the probability that a pipe dream is going to have these kind of red endpoints of horizontal pipes, and then these endpoints of the vertical pipes. So for example,
what are X and Y? I missed that.
X and Y are just a bunch of variables. They parameterize the spectral parameter of every square, which affects these probabilities. Okay, and so one thing I want to require, which is what comes out of the definition, is that P3 has to terminate, the pipe at P3 has to terminate somewhere on the right boundary, because if it terminates at the top, then it would contribute to the vertical boundary conditions, which are fixed. So that's it. That's the main result. And well, that's the definition. And now here comes the main result. The main result, that's called the flip theorem. It tells you that one probability is equal to some other probability. The first one is the one I just defined. So you fixed some horizontal and vertical boundary conditions. And then that probability is equal to a similar probability where you preserve your vertical boundary conditions. P4 is connected to Q10 as usual. And then the horizontal ones you rotate by 180 degrees. So this pipe that was on top now becomes here at the bottom. So the claim is that the sum of all probabilities of pipe dreams satisfying these horizontal and vertical boundary conditions equals to the sum of probabilities of all pipe dreams satisfying these horizontal and vertical boundary conditions. But one thing you have to do, you have to reverse the y variables. So here you can see that the y's are going from top to bottom as opposed to here. Let me give you an example of this result. let's say I take, here's the theorem again, and then let's say I take a 2x3 rectangle, and then I choose some particular horizontal and vertical boundary conditions, and then it turns out that I'm going to have only 2 pipe dreams contributing to the left-hand side and only 2 pipe dreams contributing to the right-hand side of the theorem. And the probability of each pipe dream is the product of these 6 terms shown below it. Every term corresponds to a little square according to these rules. And one thing you can immediately, well, not immediately, but you can notice by looking at these, by multiplying these things, is that all of these 4 products are going to be just different completely. No 2 of them are going to be equal to each other. And therefore, therefore this theorem is not at least completely trivial. There exists no weight preserving bijection that proves the flip theorem. And yet somehow, if you take the sum of these 2 products, you're going to get the same answer as if you take the sum of these 2 products. So that's the magic of the Yang-Baxter equation somehow. Somehow it makes this whole, there's some tricky constellations going on inside this theorem. And one curious corollary I want to mention, which you can get by taking a clever limit of these variables, is that not only the sum of the probabilities on both sides is the same, but also the actual number of pipe dreams, which contribute to the left and right-hand sides, is the same. And and this is completely combinatorial. There is I'm not using this formula for the spectral parameter in any way, just the 2 sets of pipe dreams have the same cardinality. So the question is, how do you prove this? I don't know. I tried and I failed, so please feel free to, that's a purely combinatorial problem. There should be a bijection. Now, this was the flip theorem. Let me also briefly mention this is kind of the fundamental result, but then there's also the most general result, which I'll try to not spend a lot of time on that. So it's called the generalized flip theorem. And here, instead of taking a rectangle, you're allowed to take any skew shape drawn in French notation. And then instead of taking these horizontal and vertical boundary conditions, I'm going to be interested in cuts. So a cut is just a line segment. You pick 2 lattice points on the opposite sides, on the opposite boundaries of my skew shape, and then you connect them by a line segment. So that's a cut. And every cut is going to give me a random variable, which is called the height function for some reason. And this random variable, it's going to associate an integer to every pipe dream. I give you a pipe dream, and then the way you compute the value of this random variable in this pipe dream is you count the number of pipes which cross my cut from left to right. Of course, they can cross several times, so the correct definition is that you count the number of pipes which start on this part of the boundary and then terminate on this part of the boundary. And in this particular case, there is 2 such pipes shown in red, and so the value of my random variable is 2. And that's it. That's the definition of this height function random variable. And so it has some distribution which a priori depends on all these x's and y's. But then one curious fact is that actually it depends not on all of these variables, but only on the subset of x's and on the subset of the y's. And moreover, it depends on them in a symmetric way. So there is 2 sets of variables which are called the supports of my cut. So support of a cut is you take a cut and then you project it down to the x-axis, and then you look at which variables are covered by your cut, and that's your horizontal support. And if you project to the left boundary, then you take the set of y's you get, and that's your vertical support of your cut.
I have a question.
Yeah.
So your initial setup is totally symmetric in x and y. So you could switch h and v, you could switch x and y, and it's still true, right?
Yeah, right. You can So the point is that you can rotate the whole picture by 180 degrees, or you can separately rotate the axis, flip the axis only, or you can flip the y's only. So that's, and this is also symmetric in the x's and the y's. Now, let me state the generalized flip theorem. First, here is a picture that is not yet the statement of the theorem, and I'm actually going to return to this picture later. But here's what's going to happen. Here I have 10 different cuts. And on the right, I have 10 other cuts. So, and then I have some transformation which moves these cuts around somehow, and also it permutes the y variables and the x variables. So in some way. That's the kind, and also it changes the domain a little bit. So you can see that the domains are actually different. Now, here is the actual theorem. The theorem is going to say that when you have such a transformation, then you have, when you have such a transformation, then two conditions are equivalent. One of them is easy to check, and one of them is hard to check. So the easy to check condition is that the transformation preserves the horizontal and the vertical supports of all cuts. Just as sets of variables, they are preserved. And the hard to check condition is that this transformation preserves the joint distribution of the corresponding height functions. So you permute the x's and the y's, and then you change the cuts, but then it turns out that the distribution is preserved. And if you look at the fact from the previous slide, then you are going to see that this condition of preserving the horizontal and vertical supports actually corresponds to just preserving the marginal distribution of each individual random variable. So because it's a symmetric function on these two sets of variables, and therefore you preserve the sets, therefore you preserve the individual functions, and then the theorem says that this happens if and only if you preserve the joint distribution, which is kind of, if you think about it, that's totally not what you would expect, because you would expect this for independent random variables, but these random variables are very much not independent. And if you have two cuts that overlap, then if you know how many pipes cross one cut from left to right, that gives you some information on how many pipes cross the other cut from left to right. There's no reason for them to act as if they were independent, but yet the theorem says that they do. And that's actually, so this theorem is pretty fragile. It breaks down if you tweak the weights a little bit, or if you choose a little bit stronger assumptions on your domain and stuff. So yeah, it breaks down immediately. Now let me go back to the picture and show you what happens there. So in this picture, as you can see, there is 3 red line segments which get rotated by 180 degrees. And there's also 2 blue line segments which get shifted by 1 step up. So, and then I permute the y variables in some non-trivial way. And so all you have to do to check the first condition is for each of the 10 cuts, you have to, so you take C1, and then you look at the vertical support. That's y 5, 6, 7, 8, 9. If you take C1 prime here, take the vertical support, that's going to be also y 5, 6, 7, 8, 9, but in some permuted way, which is fine. So, and then you check it for all of the 10 cuts, and then you deduce that the 10-dimensional distribution of this vector of random variables is preserved. Let me now compare theorem 2 to the flip theorem. First of all, they compare as follows. Theorem 2 implies theorem 1. And the reason is that if you take a rectangle and then you can draw all possible vertical cuts and all possible horizontal cuts, and then that information is going to be equivalent to this information of horizontal and vertical, knowing all horizontal and vertical pipes. Now, theorem 2 implies some other things. For example, it implies basically all of the results of this paper, which is 100 pages long. So it's pretty cool. And actually, it confirms a conjecture of the authors of that paper. But I prefer Theorem 1, but Theorem 2 has more probabilistic applications, I guess. But Theorem 1, actually, so the shift invariance in this paper is a certain transformation which you're allowed to take one cut and move it one step up for the price of swapping two y variables. And then it turns out that this particular transformation is just a double flip. So you apply a flip on a bigger rectangle and then in a slightly smaller rectangle, and that gives you the shift transformation, which they used to deduce many asymptotic results for other models, which were open problems before. Now, Theorem 1 has a pretty short proof, and the proof is basically a combination of two ingredients. One ingredient is classical, that's the Yang-Baxter relation, and the other ingredient is new. So that's there is a simple way to recast the six-vertex model in terms of the Hecke algebra dynamics. And in fact, in this interpretation, the probabilities of the six-vertex model actually are coefficients of a certain basis of the Hecke algebra called the Yang-Baxter basis, introduced in this LLT 97 paper. And so, so that's kind of one application of the Hecke algebra, and also Hecke algebra computations actually. So the proof of Theorem 2 is pretty long and technical, and it relies on the Hecke algebra computations a lot as well. And another application of this Hecke algebra approach is that it proves another nice symmetry, which actually, I mean, this is a pretty striking symmetry due to Borodin and Buffetov, and that's the reason I first started looking at these objects, because this is pretty cool. It works for ASAP and other things, and that's totally an unexpected symmetry, which becomes manifest once you translate things into the Hecke algebra language. This was also, by the way, discovered by Buffetov around the same time as I did it. So let me now kind of switch gears a little bit and try to be more relevant to this subject of this conference. And so I'm gonna try to explain Positroid varieties. I was hoping this would be defined by now, but I guess I have to define the Grassmannian. So the Grassmannian is a set, is the space of all k-dimensional linear subspaces of R to the n, or C to the n, or your favorite field to the n. And then, in other words, if you have a subspace, a k-dimensional subspace, you can pick a basis that's going to be k vectors in Rn, and then you can write them as a matrix. It's going to be a k by n matrix. It's going to have full rank. If you choose some other basis of the same space, it's going to be a different matrix, but those two are going to be related by row operations. And so this Grassmannian space was stratified by Knudsen, Lam, and Speyer, building on the work of Alex Pasnikov, into Positroid varieties. So these are some sort of smooth subvarieties of the Grassmannian. And then out of all these pieces, there's one piece that's open and dense. And there's a top dimensional piece, which is what I'm going to be mostly interested in this talk. That's the top Positroid variety. And the way it's defined is you take the subset of the Grassmannian, where instead of taking all possible matrices, I'm going to only take those for which any k cyclically consecutive columns form a basis. So here by delta I denote the Plücker coordinate. So it's the maximal minor of my matrix with a given column set. And so I ask that the first k columns form a non-zero determinant, and then the second k columns form a non-zero determinant, and etc. At some point, it starts wrapping around the circle. So the last non-zero minor is n, 1, 2, up to k minus 1. And that's it. I ask that these are all non-zero, and that defines a Positroid variety. Let me give you an example. Let's say I take two-dimensional planes in the four-dimensional space. Then because my first minor is non-zero, I can apply the row operations uniquely so that the first k columns form an identity matrix. And then the rest of the entries are something arbitrary, but they have to satisfy these other conditions that these minors are non-zero. And so in this case, for example, the determinant of this matrix is non-zero, which means that negative A has to be non-zero. And then the determinant of this matrix is non-zero, so AD minus BC is non-zero. And then there's one more matrix, which you get by wrapping around a circle, and its determinant is D. So D also has to be non-zero. And that defines the 2-4 Positroid variety. And let me ask maybe a weird question for now, but let's see. Question is how many, let's say I take a field with Q elements and ask how many such matrices exist over FQ. And in this case, it's pretty easy to count, right? You have A is non-zero and D is non-zero, so that's Q minus 1 squared. But then also BC has to be not equal to AD, and AD is non-zero, so BC has to avoid it. Yeah, anyways, you can count the number of pairs BC, and that's this expression here. And so then it's easy to check that. Let me just rewrite this left-hand side in a more convenient way for me. So that's the answer, how many matrices over FQ in the top Positroid variety. Now let me try to go back. I'm done with Positroid varieties for now. Let me go back to the six-vertex model. And then here I have, what I'm going to try to do is I'm going to try to send all the y variables to 0. And if I send all the y variables to 0, what's going to happen is that the y's here are going to get sent to 0. And so the spectral parameter is going to be just equal to 1 over q in the limit. And therefore, all these 4 probabilities are going to be 1 over q, 1 minus 1 over q, 1 and 0. And so, and this 0 is actually interesting. Right? The 0 is telling you that once 2 pipes have crossed, they are not allowed to touch anymore. They can cross back, and then they can touch all they want, but then once they cross back, they are not allowed to touch again. So that's a very weird condition, but that's what happens when you send y to 0. Now let me try to compute something. Let's say I'm interested in the, let's say I take a k by n minus k rectangle, and I'm interested in this probability that my pipe dream, the corresponding permutation is the identity permutation. So I send y to 0, and then I ask what's the probability of the identity permutation. And for example, when I take k equals to 2 and n equals to 4, so I have a 2 by 2 rectangle, and then there's always this trivial pipe dream, right, where there is only elbows, no crossings. It always contributes to this value here. But in this case, there's one more pipe dream which has a double crossing, and their probabilities are given below, just obtained by multiplying the numbers in this table. And therefore, the answer is just given by taking the sum of these two expressions. That's the probability of the identity permutation. Okay, now where am I going with this? Let me try to put these two examples on the same slide. So here's the number of points in the Positroid variety, given by this formula. Here's the probability of the identity permutation in the six-vertex model. It's given by this formula. These formulas look kind of similar. If you look closely, they're actually very similar. And that is not a coincidence. So that's a result. The result is that you can obtain the point count in the Positroid variety as just q to the dimension of the Grassmannian times the probability of the identity permutation when y is equal to 0. And let me actually give you a proof of this proposition. And the proof goes as follows. It has 2 steps. So the first step is you look at this table closely, and then the second step is you look at this paper closely, and then basically you're done. Because what happens is this weird condition I told you about is actually, it's known as Deodar's distinguished subexpressions. And what's surprising is that all these other weights correspond exactly to the weights in this paper of Deodar. And this paper of Deodar was, he was interested in computing these Kazhdan-Lusztig R polynomials, and then this number of points in the Positroid variety is a particular example of the Kazhdan-Lusztig R polynomial. And so, that's how the proof goes. And one kind of remark I want to make is that this whole thing, this statement generalizes to all Positroid varieties, not just the top dimensional one. You can take any Positroid here, and then you're going to have to take other permutations here, but then the result is proven in the same way. Okay, now while I'm here, let me mention something that I'm very excited about, which is, let's say you have that these two numbers are equal, and that's pretty nice, but can you actually compute one? Each of them is some polynomial in Q, which for each k and n, I have a polynomial in Q. What's that polynomial? And the answer is that you can, and that's a joint theorem with Thomas Lamb, which is not yet on the archive. So let's say I assume that the GCD of k and n is 1 for simplicity. Then the claim is that this point count of a Positroid variety is this trivial power of Q times the Q Catalan number, the rational Q Catalan number, which is given by this formula. That's the Q binomial coefficient. And yeah, so that's the rational Q Catalan number. This is divisible when GCD is equal to 1. And as many of you know, if you just count the points in the whole Grassmannian over FQ, that's just going to be the Q binomial coefficient. So you can divide both sides by this number, and then you get an alternative description of this formula, which is kind of another probabilistic interpretation of this number. And this is saying that if you take FQ to the n, and then you choose a random k-dimensional linear subspace, the probability that it belongs to the top Positroid cell is given by this formula here, which is, by the way, clearly less than 1, so that's good. And yeah, so the proof of this theorem, the only proof that we know, is using knot theory. Somehow, yeah, the story is that we had spent more than a year, Thomas and I, trying to prove this, and we just failed. We failed miserably, and I was whining the whole time. I was saying that, like, if I go to FIPSEC and present this theorem there, then somebody's going to prove it within a week combinatorially. And I think Thomas disagreed with me, so I would very much like to encourage everybody to try and prove this. If you succeed, then Thomas will buy me a chocolate or something like this. And so there are some partial combinatorial results toward this goal, and notably David Spire. So for the case Q equals to 1, David was able to, if you send Q equals to 1, then this is 0, but then if you kind of factor it out, then the rational Catalan numbers are well defined, and then special cases of those are Catalan and Fuss Catalan numbers, which happen to satisfy a recurrence relation, and then David was able to use this recurrence relation to prove the result when Q equals to 1. And Thomas and I actually know how to do this for all k and n when Q is equal to 1 combinatorially. So that's actually a nice thing about this. We can do this for all Positroids, and then Positroids are nicer than these rational Catalan numbers because rational Catalan numbers don't satisfy any recurrence relations. And for Positroid, you kind of embed Catalan numbers in this larger family of Positroids, and then those satisfy relations, and therefore you can actually compute this for all k and n. But for general Q, all we know is using knot theory. So there's a knot invariant, which there's an easy way to associate a knot to every Positroid variety, and then the Humphrey polynomial that knot gives you the point count. And so why are Thomas and I interested in these things? Not because we want to know the number of points in this Positroid variety, but there's a kind of bigger goal behind the scenes, which will hopefully happen this year. Hopefully, I don't know, but the grand goal is a Qt version of this result. So many of you know that there's this famous Qt Catalan numbers. That's the right-hand side, and then for the left-hand side, instead of taking the point count, you have to take the cohomology of cluster varieties. That's a paper by Thomas and David. And so the cohomology, like the Poincare polynomial, gives you a one-variable polynomial, but then there is a mixed Hodge structure, which is based on results of Deligne, that gives you a polynomial in two variables. So, and this works for cluster varieties. So you have to know that Positroid varieties are cluster varieties, and that was actually done by Thomas and myself pretty recently. So by building on the work of Serhienko, Sherman, Bennett, Williams. And the point is that if you combine these two papers, then basically you get a Qt polynomial for every Positroid variety. It's Qt symmetric and unimodal. It's very nice. And so we want to, and then the main idea is that we want to categorify this proof to get the Qt version. So many of you know that the non-invariance can be categorified. That's Kalmanov-Rosansky homology. And then that's the right-hand side. And for Positroids, we have a Qt version coming from this cohomology. And so you can relate the two constructions together through mixed equivariant derived category of perverse shifts, which then connects to Rukia complexes of Zorgio bimodules, and then you're done basically. So that's the kind of easy part of the construction. Let me try to go back to the six-vertex model. I don't have much time, but what I wanna say is that if you take the six-vertex model, then you can send y to 0 and get something interesting, where you can also get from taking Positroid varieties in the Grassmannian. And so, question: is there a common generalization? And the reason I'm asking that is because sometimes you can send y to 0, and then the phenomenon for the six-vertex model lifts to the Grassmannian level. So for example, if you take the flip theorem, the main result of the stock, then you send y to 0, you get that the number of points in two subvarieties of the Grassmannian two subvarieties have the same number of points. And it actually turns out that it lifts to the Grassmannian level because these two subvarieties are actually isomorphic over any field. And also, not only the flip theorem, but also the proof of the flip theorem lifts, which was using the Yang-Baxter and Hecke algebra, but the proof is some kind of recurrence based on these two ingredients. And that recurrence turns out to also have been studied for the Grassmannian. That's the recurrence from the paper by Müller and Speyer, which they used to show that these cluster algebras are locally acyclic. So let me kind of put two pictures on the same slide. On the left is the picture from this paper by Greg and David. And these are Plasnikov's diagrams. There's Playback graphs, which are kind of in the background, for which there is a dimer model attached to them. So I think I said all the words from the conference title at this point. And then they have some recurrence for V in terms of VSI and SI-VSI. And here's a picture from my paper. That's the induction step in the proof of the flip theorem. I act by some simple transpositions on the left and on the right of my horizontal boundary conditions. And it turns out that this is literally the same recurrence. It's in completely two different worlds, but the recurrence is just literally the same. So question is, can you generalize these two objects to some common ancestor? There's two more questions, which I think I'm out of time. So one question is clarify a relationship with pipe dreams. Another question is that there is another recent paper which has similar results in completely different kind of class of models. And in that paper, the fundamental transformation is the geometric RSK, while in my paper is the flip theorem. And they play kind of the same role in the proof. So question, is there some way is the flip theorem literally the same as geometric RSK if you look at them from the right point of view or not? And that's it. Thank you very much.